Hello everyone. The chapter 1 of Dieter, which is the introduction part. So this will tell you about the introduction of the book, like why this book is there. So what is the scope of this book, Mechanical Metallurgy? So guys, Mechanical Metallurgy will let you study the mechanical related thing, right? Mechanical related things in metallurgy. So that will deal with like forces, okay, deformation, okay, stresses, pressures, this thing. So this will tell you that if you do some mechanical work, like we put some force, then what will be the response of that material and how the deformation will happen, either it is elastic or plastic. So these things will be dealt over there, over in this chapter. Then what is the assumption when we study this mechanical metallurgy? The assumption is that suppose there is solid. So we initially assume that this solid is homogeneous. Okay, homogeneous. That means the amount of defects which are there na, that should be very low. Okay, and the structure is very homogeneous, but practically it is not so. But at least we can assume here for the sake of simplicity that the material is homogeneous. Okay, now here is a simple concept which has been given, that is the elastic and plastic deformation. Okay, so what do you understand by this elastic and plastic deformation? So we understand that we all have heard about this stress strain curve, right? This is your stress and this is your engineering stress, right? And this is your engineering strain, right? So up to this limit we consider that the material is elastic. That means if we stretch this material, suppose this is fixed in a wall and we are stretching this, so after stretching, suppose this has elongated, okay, but once we cut this stress, then it returns back to its original dimension. Okay, here we remove this stress. Okay, then it is called elastic. Now suppose we are stretching, okay, and it has stretched up to this limit, but after removal of load we are getting this some permanent deformation. Okay, so when we get some permanent deformation, then it is called as plastic deformation. Okay, and one thing is to be noted, that here the stretching was up to this limit, but after removal of stress we have got the stretching up to this limit, that is although lower than the initial stretching but higher than the initial length. Okay, so that means here what is happening is that the material is also getting try to get back to the original position, but that limit is up to the elastic limit, right? That means here elastic recovery happens, but that elastic recovery is not so because it has been permanent deformed also. What is the permanent deformation? This limit. And what is the elastic deformation? This limit, right? So elastic recovery also happens when we go beyond the plastic region. Okay, so this is how we can understand. This is your stress strain curve. Now suppose I put stress up to this limit, then when I uh, remove the stress, then see at that point of time during the application of the force, the strain is this value, right? That is epsilon 1. Okay. Now when we remove the stress, then what happens? This return back in the parallel to this elastic line. So once it return back to the parallel, so that means this strain is the permanent strain. So epsilon permanent. So this strain which is getting recovered, so that is elastic. Okay. So in every plastically deformed material, there is a elastic recovery which happens. Okay. Concept of average stress. Okay. So guys, in the case of a stress strain curve, the stress which we write, that is the average stress which we write. Okay. So how it is? So let us see over here. Okay. Now in the book, if you see, then suppose this is your specimen, which is we are trying to elongate with the some force, that is P. So the pressure P, the load. Okay. Force or load. Okay. So P is the load, and when we do the tensile testing we do elongation, then we generally mark initially the 2 points, and for the tensile testing the gap is 50 mm, right, the standard one. So once we applying this stress, okay, or this force, sorry, once we are applying this force, we apply force, right guys. The point is here that we always apply force. A tensile machine only applies force, nothing else. The stress is a response of this force. Okay, so this is the initial length. Now after some time application of some force, then what happens? This is the new length. Okay, suppose this is L, and initially the length was L naught. Okay, so what is the change in length? It is L minus L naught. Okay, and what is the initial length? It is L naught. Okay, so the strain we define in terms of change in length divided by the original length, and since here it is length and length, so it will be dimensionless. Fine. Okay. Now see, here we are applying a force, right, and this system should be in equilibrium. Okay, so if we see the free body diagram of this specimen, then this is the P which is being applied. Okay, that is the load, and in response what happens, this body in response to this force, it generates a stress, that is sigma, and it is distributed over this complete area, that is A. Okay, so sigma integrated dA. Okay, or we should write like, so in response to this force P, there is a stress which acts in the area A, and it is like sigma TA. So this counterbalances this force. Okay, now what happens, this sigma, that is the stress which is there, so to have this value as a single value, that is the constant value, what happens, suppose this is the cross section, right, and this force P is being applied. So the material should be such that it should be completely homogeneous deformation, such that the same value of sigma it is giving at every location, right? But it doesn't happen so. Why? Because you can see, suppose here the grains may be bigger, the grains may be smaller, the orientation of grains may be different. Okay, then suppose in this region there it can be such that some defects are there, some things are there, some inhomogeneity are there. So that's why the stress which is here, we should assume it as the average stress. Okay, so once we assume this as average stress, so from this we can say P is equal to integrated sigma dA. So this implies P is equal to sigma dA, because sigma is equal to average stress we have assumed, and this average stress will be a constant value. So this implies P is equal to sigma into A. So this implies sigma is equal to P by A. Okay, that means the stress will be equal to the force applied divided by the area. Okay. Guys, next we'll discuss the tensile deformation of ductile material. Okay, so see, this will be your stress axis, this will be your strain axis. And what is the curve it looks like? Right? This is something like this. Okay. So guys, now this is the stress strain curve. So what happens? This is your yield point, right? But can you clearly define what is the yield point? So this is the problem which happens in the case of most of the ductile material. So we take a offset, that means a permanent strain, because that permanent strain, that point if you mark, then it is marked as suppose 0.2% strain. Okay, or sometimes in some books we also see 0.1% offset strain. This is also called as 0.2% offset strain. Why offset? Because we just draw parallel to this line, this elastic line, so that is called as offsetting, right? Once we draw a parallel line to some line, then that is called as offset. So 0.1% strain is also in some cases, okay, but generally in the most of the cases it will be 0.2%. Okay, so this 0.2%, that means 0.2%, so what will be the strain value? 0.002. So you can see very low strain. Okay, so suppose we have here, so this point will be considered as yield point. Okay, that means beyond this we are getting plastic deformation. Okay, and up to this we are getting elastic deformation. Okay, but ideally if you see, there is some permanent deformation just before this, that is of 0.002, but that is to take a boundary. Okay, so we can assume that up to this limit we have a permanent the elastic deformation. Okay, what is the next thing? So what happens if we keep on increasing the stress, then if we keep on increasing the force, right, if we keep on increasing the force, so it is seen that the stress is also increasing in the case of plastic deformation, but it goes to a upper limit. Okay, and this upper limit is called as UTS, that is ultimate tensile strength. Okay, everyone. Now after this UTS, this maximum limit, it again starts decreasing and decreasing, and finally it breaks at some stress, that is the last stress which the material holds. Okay, so this is called as the fracture stress. Okay, okay guys. Now guys, just tell me that suppose this is the UTS point and this is the fracture point. Okay, so now the UTS is greater, right? UTS is greater than this YS, that is the yield. So the stress here, it is called as yield stress, right? So why this UTS value is greater than yield stress? Or is it completely true every time that UTS will be always greater than YS? Huh? Yes, UTS will always be greater than YS for a metallic material. Okay, but for a perfectly plastic material, it can be just equal to UTS. Means yield strength can be equal to UTS. Okay, but it will be never be that yield strength is greater than UTS. ये कभी नहीं होगा. ठीक है, for a perfectly plastic material. Okay, so we can get that yield strength can be equal to UTS, but there is no any perfectly plastic material, no any perfectly plastic material. Okay, that is just an assumption. So why this UTS is greater than yield strength? It is greater than yield strength because at that point of time the plastic deformation happens. So once this plastic deformation happens, that means dislocation generation happens. And when more number of dislocation generates, so the two dislocations come together and they lock each other, and it decreases the mobility of further dislocations. Okay, so this is because of this dislocation generation. So we'll discuss later on that how, what kind of dislocation it forms. Okay, so guys, for today let it be up to this point. So we will come with the next section. Okay, and we'll discuss. So thank you all.